Good morning, student. In previous lecture we start with the new chapter, that is LQG controller, and in this chapter we studied the introduction about the controller and the design approach, that is spectral factorization. In today's session we use this approach, that is spectral factorization, to design the LQG controller. Now let's see the design method. Here we apply the transfer function approach to design the LQG controller. Consider a system of the form, that is A of Z inverse into Y of n is equals to B of Z inverse into U of n minus k plus C of Z inverse upon F of Z inverse into zeta of n. This is the same equation which you have studied in identification chapter. In this, Y of n is the output, U of n is the input, and this minus k is used to represent there is a delay of k unit in the system, and zeta of n represent the noise. In previous chapter, that is identification, we use f of z instead of f of z inverse. Here we have used f of z inverse. The reason behind is that we have allowed that f has 0 on the unit circle, so that we can handle the step disturbances very effectively. But as this f has 0 on the unit circle, therefore the zeros of f of z inverse can have its 0 inside or on the unit circle, so that we can handle the disturbances, that is step disturbances, very effectively as compared to f of z. Therefore we can use here f of z inverse instead of f of z. Now our main aim to design a controller U of n that minimizes the performance index, and the performance index for this controller is given as j is equals to, this is epsilon is a function, j is a function of epsilon, is equals to into bracket v of z inverse into y of n bracket raised to bracket square plus rho into w of z inverse f of z inverse into u of n bracket square. This is the performance index for the LQG controller, and as compared to this performance index is different as compared to the which you have studied in previous chapter. In this polynomials, you have seen the new polynomials, that is v of z inverse, w of z inverse, and f of z inverse, and these polynomials are provided in this performance index to provide the flexibility. Now we see what is meant by this v of z inverse, w of z inverse, and f of z polynomials. While designing the controller, our main aim is to minimize the error. As error is minimum, the control effort which is given by the controller is equals to 0. That is mean u of n minus 1 is equals to 0. That is we wish only the rate at which u of n changes to be minimized. That is, we have to minimize this difference. That's why here we choose w of z inverse is to be 1 of z raised to minus 1. Now we can suppose the disturbance comes in steps. That's why we have used f is equals to 1 minus z inverse, as this f is denotes the noise term. Therefore we use this as a 1 minus z inverse. Now we can't control the absolute value of u of n. That's why we can make the constraint on delta u of n instead of u of n. From this previous discussion, we can say that v and w are provided for the flexibility to solve the performance index, and f is used to make the problem simple. Here you can see the performance index, and this performance index is same as that of we have seen previously. That is, this is the same performance index is reproduced there instead of the argument z raised to minus 1. Here you can see this is the same as we have seen earlier. Now we have to minimize this performance index. While minimizing this performance index, here in LQG controller design we have used another method, that is variational method. to minimize this performance index. For this, let's see how we minimize this performance index. Suppose that there is a controller of the form, that is u of n is equals to minus s into z raised to minus 1 divided by rc into z raised to minus 1 into y of n. This is the transfer function of the controller, and with the help of this controller we have to minimize this performance index. But in variational approach method, we look for another controller transfer function instead of this. Therefore, here you can see u of n is equals to sc into z raised to minus n minus 1 divided by rc into z raised to minus 1 into y of n plus tau into z of n. This is transfer function, means this control effort is different from this control effort. The additional term included is tau into z of n. Due to variational approach, this extra term is added in the transfer function of the control law. Here we come with the new control effort. Now let's see. In previous equation, we have to find RC, SC and T such that the increase in the performance index should be equals to 0. And let's see how we find this RC, SC and T. We put this control effort, that is u of n, in previous equation. That is, we have to put u of n. We have to put the value of u of n in this equation. Then we come with the new equation, that is, here you can see a of n is equals to z raised to minus k into b into bracket minus sc into rc y of n plus tau into z of n bracket complete plus c of f c by f into z of n. Here we put, instead of u of n, we have put the value of u of n from this equation. That is, from this equation we have just put the value of u of n here. Now we simplify this equation, and while simplifying this equation, we come up with the this equation, that is y of n equals to c into rc divided by f into alpha into z of n plus z raised to minus k b into rc divided by alpha into tau into z of n. Now here I give the solution how this equation directly come from this equation. That is, here you can see y of n is equals y of n plus we have just collect the terms of y of n. That is, means we have just transfer this term from this side to left hand side. Here you can see, and here we write the remaining term, that is z raised to minus k into b into tau of z of n plus c by f into z of n. Here you can see we write the remaining term on the right hand side. Now here we take the y of n common and we write the remaining term here. The right hand side is same as it is. Now we here from this RC here write with the a, that is, it comes out a into RC plus z raised to minus k b into SC divided by RC. We assume that this a into RC plus z raised to minus k into b into SC is equals to alpha. We have put, instead of this whole term, we have just assumed it is equals to alpha. That's why this equation comes as y of n into alpha by RC is equals to c by f into z of n plus z raised to minus k b into t into z of n. Here you can see y of n, we have just multiplied by RC and divided by alpha. That's why it comes as y of n is equals to RC into c divided by f into alpha into z of n plus z raised to minus k b into RC divided by alpha into tau into z of n. We have just take these two terms on the right hand side. That's why this RC becomes multiplied and this alpha becomes divided by terms. Therefore here you can see this is the same equation as it is. I have given the just solution, that how from this equation how to get this equation. I have just give the solution here. Here alpha is in the denominator, and it represents the characteristic equation of model. Therefore, as alpha represent the characteristic equation, therefore we can say that the zeros of f of alpha, that is zeros of alpha, should be on the unit circle. Now here you can say here what is we have write what is meant by alpha, and alpha make the characteristic polynomial. Therefore we said that it's 0 inside the unit circle. Now we write the y of n as here. We generalize this equation. Y of n is equals to y0 of n into delta of y of n. Now what is meant by y0 of n and delta y of n? Here we have mentioned y0 of n is equals to c into rc divided by f into alpha into zeta of n. And what is meant by delta y of n? Z raised to minus k b into rc divided by alpha tau into zeta of n. Here you can see this is meant by delta of y, and y this by y0 of n, and this is delta y naught of n, delta of y of n. We can just use the names to represent this term. Now here delta y of n is the variational term because the variation occurs in this delta of y of n is due to the variable tau, which is as tau changes, this delta y of n changes. Now we have just put value of y of n, that is this value. We have just put this value in previous equation, that is in this equation. Here we have just put the value of u of n. Now this u of n becomes, here you can see minus sc into rc. We have just put value of y of n, that is we have calculated earlier, and this plus tau into zeta of n. Now we solve this term, that is u of n is equals to minus sc into c. This rc and this rc gets cancelled, and it remaining with the f into alpha into zeta of n plus z raised to minus k beta rc. As we multiplied this term with this term, then rc get cancelled. The remaining terms are z raised to minus k b into sc divided by alpha, and we have just take common tau into zeta of n. That's why here plus 1 is come, and the common term is right here, tau into zeta of n. Now here u of n is equals to minus sc into f of alpha into zeta of n. It is same as it is, and plus we have just write this alpha, that is it comes out to be z raised to minus k beta sc plus alpha divided by alpha and tau into zeta of n. Now instead of this term, here we assume that alpha is equals to rc into a plus z raised to minus k into beta sc. Now this alpha, here one sign mistake is there. Here minus z raised to minus k into b of sc. Here you just correct the here instead of here minus term should be present, that is it comes out to be alpha minus z raised to minus k beta sc, and instead of this term, from this alpha, as we have put this into the left hand side, it comes out to be alpha minus z raised to minus k beta into sc is equals to a into rc. Means instead of this term we write a into rc. Therefore instead of this term we have just write rc into a divided by alpha, and the same equation is as it is. Now this can be simplified as u of n is equals to u naught of n plus delta u of n. Then what is meant by u of n and delta u of n? We have just put here we have put this all term as a u of n and this term as delta u of n. Here you can see what is meant by u naught of n, minus c into sc divided by f into alpha into zeta of n, and what is meant by delta u of n is equals to rc into a divided by alpha into tau of zeta of n. We have just mentioned the what is meant by u of n is equals to delta u naught of n plus delta u of n. Now with the help of this control effort, we have to minimize the performance index. And how to minimize this performance index, we will see in the next lecture. Good afternoon, student. In today's lecture, we will start with the LQG controller design part 2. But before going further, we have just to make brief revision on the previous lecture, which we have studied. In previous lecture, we studied the performance index for the LQG controller. Here you can see this is the performance index for the LQG controller. This performance index is different as compared to the previous, performance index which we have studied in previous chapter. We have to minimize this performance index, and for this we have to design the control effort U of n. Here you can see the performance index for the LQG controller. To minimize the performance index, we have used variational approach method. That's why this additional term is included in the control effort. With the help of this control effort, we have to minimize the performance index. Now with the help of this U of n, let's see how to minimize the performance index. Now up to this you have studied in previous lecture. From this onward we will start. The performance index J is equals to, we have just put the value of y and U of n. Here you can see previously what is meant by y. Y is nothing but y naught of n plus delta of y of n, and at the same time U of n is nothing but u naught of n plus delta u of n. We have to just put value of y of n and u of n. Here you can see, instead of y is equals to y naught plus delta of y, and u is nothing but u naught plus delta of u. We have to expand this bracket, and with the expansion we have to get y naught square plus 2 into y naught into delta of y plus delta of y square. At the same time this remains as it is up to this, and we have to just expand this bracket, and with expansion we have to get this matrix, this bracket, and we have to generalize this whole equation as J is equals to J0 plus 2J1 plus J2. Then what is meant by J0? J0 is nothing but this is epsilon. Epsilon is used to represent the J is a function of epsilon, therefore here epsilon is used. Here you can say what is meant by J0. J0 is nothing but epsilon of V into Y naught bracket square, means this term plus epsilon into epsilon rho into epsilon of W of F into U naught bracket square, means this we have to multiply this term in bracket, then we have to get rho into epsilon W square into F square into U naught square. We have to collect these two terms, and we call it as a J0. Then what is meant by J1? J1 is nothing but, here we have used 2J1, means J1 is nothing but this y naught delta of y and u naught into delta of u. Here you can see v into y naught into v into delta of y plus rho into epsilon w of u naught into w of delta u. On collection of these two terms we have called it as a J1, and J2 is nothing but the remaining term, that is delta of y square and delta of u square. Here you can see delta of y square into delta of u square. Now as J0 and J2 are sums of square, means here you can say here J0 and J2 are terms of square, means it contains terms with the square. Therefore they can't be made 0. On the other hand, the terms J1, that is the terms which are included means the terms of J1, that's why we can't equate J0 and J2 equals to 0 due to the square term. Therefore we have to make J1 equals to 0. Our main aim is to minimize this performance index, that is mean J is equals to 0, but we can't equate J0 and J2 is equals to 0. That's why we have to make J1 equals to 0. That's why what is meant by J1, previously you can see here, wait, here what is meant by J1, we have to make this J1 equals to 0. Here we put J1 equals to 0, that's why here this term is equals to 0 is come here. Further we have to put value of y0 and delta of y and u of u0 and delta of u in previous. Here you can see what is value of y0. We have to put instead of y0, and instead of delta of y of n you have to put this value, and at the same time instead of u of n you have to put this value, and delta of u of n you have to put this value. And with the use of this term, our performance index becomes as this whole. We have to put all the values of y0, delta of y, u0 and delta of u. With the replacement we have get this equation, and we have to equate this all terms is equals to 0. Now this whole equation can be written as closed loop integral. The same equation is written as it is. Here we have to use the spectral factorization method to design the LQG controller. Therefore we require the polynomial in terms of z as well as z inverse. That's why we have to convert this v, b, r, rc polynomials into z from z inverse. That's why to differentiate these polynomials are in z inverse, and these polynomials are in z, power of z. To differentiate these two polynomials we have to use only v star, b star and rc star. These polynomials in powers of z, and to convert from a of z inverse into a of z, we have to just replace z raised to minus 1 with the help of z. That's why here z raised to minus k becomes z raised to plus k. And at the same time we have to also convert this whole equation into a of z. This represent a of z inverse, and this represent a of z. We have to require these two polynomials. We have to just make some arrangement, and we have to make this as a of z. Now here it is mentioned that the start variable are function of z. As I said earlier, these are the function of z, that is v star is nothing but v star of z, while the unstarred variables are function of z inverse. For example, sc is equals to sc into z raised to minus 1, means star polynomials are in the function of z raised to 1, whereas this unstarred variable is in the polynomials is in the function of z raised to minus 1. From this we have just generalized this equation as it is here. As we have said earlier that alpha is a characteristic polynomial, and for the systems to be stable, the roots of the characteristic polynomial should be positive. Therefore we can say that alpha is a characteristic polynomial, and that's why it zeros inside the unit circle, means its zeros lies inside the unit circle. That's why thus when we divide this whole term with z f into alpha, then due to this characteristic polynomial we can say that there is no residue term within the unit circle. As f has 0 inside the unit circle, from this we can say that there is no residue term within the unit circle. Hence as there is no residue within the unit circle, then due to this we can say that this whole integral term can vanish, means this whole integral term can vanish. Due to this vanish of integral term, we can generalize this equation as here you can see, due to this as integral term vanishes, we can write the previous equation as it is. Here we just take the denominator in the right hand side, and we have just introduced one polynomial x. We have just introduced one new polynomial, that is x star. Here mentioned that x star is an unknown polynomial, and from this and this right hand side we have expand this equation further. While expanding, this right hand side term remains as it is. Here you can say z into f, instead of alpha we have just replaced the value of alpha. This value of alpha means we have studied in earlier lecture what is meant by alpha. Alpha is nothing but rc into a plus z raised to minus k b into sc into x star. Now we have to collect the terms of rc and sc separately. Here you can say this term consists of rc, at the same time this term also consists of rc. We have to move this term from right hand side to left hand side. Now we take rc common and the remaining terms are right in bracket. At the same time this equation means this term consists of sc and this term also consists of sc, and we have take the f into sc. Here we have take f into sc common, and we have to write from these two terms we have write the remaining terms, and we get this solution. As you see, rc and sc represent the control effort. Means while designing the control effort you come across the transfer function, that is u of n upon y of n is equals to minus sc divided by rc. Means from this we can conclude that rc and sc are co-prime. Means while suppose this co-prime means there is no common term between the two polynomials, that is rc and sc. This is conclusion is referred as because suppose there is a one term is common between the two between these two polynomials, then this there is a cancellation occurs, but our control effort should be stable. Therefore we can say that there is no common term present between rc and sc, therefore we call it as a co-prime. Means there is no common term present between rc and sc polynomial, therefore we can say that rc and sc are co-prime. Therefore from this we can two sides of the above equation should be equal to the rc and sc into k star. Here k star we have introduced another variable, that is k star is a polynomial in z into z inverse. Now we have to just divide this whole term with the help of this term. Means this term we have to move this right hand side, and here we can get this term divided by this term is equals to rc by sc, and here you can see this whole term is nothing but k star into rc. Means we have to just divide this term with the help of this term, and we get equals to rc by fsc. We have to just here you can see we have to get these two terms by comparing these two terms here. Now we have to multiply this equation, this first equation with the help of a. Means we have to multiply this equation with a, and the second equation we have to multiply with z raised to minus k into b. Now we have to multiply, and then we add the two equations. While multiplying and adding we get the result as this c into rho into a into w f star w star a star plus b into v star b star is equals to k star into alpha. Now how we get this equation? Here you can see as we multiply this equation a, here we have multiplied the equation a, and at the same time we have multiplied this equation z raised to minus k into b. Now while adding we have to multiply we have to add the left hand side at the same instant we have to add the right hand side term. While adding the left hand side term we remaining with this first term and the second term, that is this term. These two terms means here z raised to minus k into plus b into b into a. Here x star, here it is x star. Here you can see this also come as z raised to minus k plus 1. This due to this z term it comes as a z raised to minus k plus 1. Means this term is same as that of this term, therefore these two terms are get cancelled. Now at the same time here you can see these two terms are get cancelled. At the same time here z raised to plus k and z raised to minus k, it comes up to be z raised to 0, means it is 1. That's why the terms remaining are this first term and the second term, only this term. And at the same time on the right hand side as we add these two terms the k star comes common, and a into rc plus b z raised to minus k b into sc, this is nothing but the alpha. Therefore we have right here k star into alpha. Next we obtain the spectral factorization of the left hand side term of the equation previously. Here for this left hand side we have to design spectral factorization. Now for this term, previously for this term we have assumed here r into beta of star is equals to this term, means we have to assume this term is equals to this term. Here r is a positive scalar and beta of z inverse is a stable monic polynomial. We assume beta is a stable polynomial, and when we consider rho greater than 0, then the stability of b is determined by if suppose that b into v, means this b into v and afw, this afw, when these two terms have no common factors with the 0 on the unit circle, then we can say that this beta term is stable. And suppose if zeta is equals to 0, then this b into v polynomial should have no 0 on the unit circle, means this two terms, means this only two polynomials should have no 0 on the unit circle. At that time this a, f and w, these polynomials, if suppose that these polynomials have 0 on the unit circle, then there is no problem, but this b into v should have no 0 on the unit circle. At that time we can say that this beta polynomials is a stable, and by using this equation this 13.39 becomes as suppose we have to put this whole term is equals to r into beta star. Therefore the previous equation, here this equation becomes as c into r beta into beta star is equals to k star into alpha. Here you can see this is the equation written here, and we have said alpha, which we have studied earlier, alpha is a characteristic polynomial, and this alpha is always stable for the system to be stable. Therefore here written as alpha is required to be stable and monic. As we assume that alpha is a stable polynomial, therefore we by comparison we can write alpha is equals to c into beta. Why we taken this as a alpha? Because we have assumed that b is a stable monic polynomial. Therefore we have take alpha is equals to c into beta, and the k star is nothing but the remaining term, that is r into beta of star. Now from equation 13.37 we say that f must be a factor of k star into rc. Here you can see f is a factor of k star into rc, and here we have just put the value of k star. K star is nothing but r into beta star, and we assume that here we assume that b star has no 0 on the unit circle, but in previous at starting we assume that f must be a factor of means f has 0 on the unit circle. Here from these two conclusion we can say that f must be a factor of rc, because f has 0 on the unit circle and b star has no 0 on the unit circle. Therefore this f is not a function of beta star. Therefore we can say that f is a factor of this rc. To represent this relation, here we have assumed we have derived that rc is equals to r1 into f. Here we represent the f is a function of rc. Now substituting for k star from equation 13.43, here we have put the value of, from this we have to put the value of k star, and rc from equation, that is from we have to put the value of rc from this equation into equation 13.37 and 13.38. Let's see, this is the equation, and in this equation we have to just put the value of k star and rc, and in this equation we have to put the just value of k star. With the replacement of this value, this two equation becomes as this equation. We have just put the value of k star into rc, as we have put k star, rc is nothing but r1 into f, but here you can see here, as we put rc is equals to r1 into f, this f and this f get cancelled. Therefore we have remain with the only this bracket. Therefore here you can see the f get cancelled, therefore it remains with only r1 term, and here we have just put the value of k star. There is no change in this equation. Now from these two equations, that is we have to solve the r1 sc and x. We have to find this unknown polynomials, and to find this polynomial we have to use these two equations and this equation. From these three equation we have to find r1 sc and x, and with the help of these three polynomials we have to design our control effort u of n. But unfortunately this relation involves the polynomials in powers of z as well as z inverse. As you see previously, we have just used the spectral factorization. To use the term spectral factorization, we have to take the polynomials in z and z inverse. Therefore further we have to convert this z polynomials into z inverse polynomial. Therefore we have to use spectral factorization. Now we have to first convert them into the polynomials of z inverse. Now how to convert this z polynomials into z inverse? Now let's see. This is the first property which should be satisfied by the polynomials A for the spectral factorization property. That is AR of z inverse equals to z raised to minus n into A of z. This property should be fulfilled by polynomial A, and n is nothing but the polynomials A is symmetrical about n is symmetrical about that is z raised to minus n. Now from this we have to just take this z raised to minus n into left hand side, and we have to modify this equation. Now by using the spectral factorization property, by using this property we have get this polynomial. Then let's see how we get this polynomial. Just to go back, here we have come with this solution, that is this equation, and with this solution we have to use the spectral factorization property. As we have seen earlier, as we have seen here, here b star means, suppose here b star is represent the polynomials into z raised to 1 plus 1 polynomial, but we have to convert into z raised to minus 1 polynomial. That's why we can replace this b star by using the property. Here you can see A of z is replaced by z raised to n into AR of z inverse. That's why here b star is replaced by br into z raised to beta. Likewise here these polynomials are already in z raised to minus 1, and these polynomials are into z raised to plus 1. Therefore we have to convert this polynomial from z raised to plus 1 to z raised to minus 1. And that's why we have to use here spectral factorization property. Now this becomes as f star becomes as fr into z raised to zf, and w star becomes as wr into z raised to dw, z raised to w. At the same time a star becomes as ar into z raised to dA. With this likewise these terms also become as v star is equals to vr into z raised to dv, and b star becomes as br into z raised to db. With this here you can see, which I said earlier, that is b star becomes as br into z raised to beta. At the same time w star, f star and a star becomes as wr fr into ar, and we have just add all the terms, that is dA plus df plus dw. Likewise this v star becomes as vr into z raised to dv, and beta star becomes as br into z raised to db. But we have collect all the terms of z, that is dv plus db. Therefore now dA plus df plus dw is greater than or equals to dv plus db. Therefore the degree of d beta is equals to dA plus df plus dw. As this this term is greater than this dv plus db term. Therefore we assume that degree of d beta is equals to dA plus dF plus dW. Now multiplying this equation, now multiplying this equation, whole equation, with the z raised to minus d beta. Therefore this d raised to plus beta minus beta get cancelled and come with the z raised to 0, that is equals to 1. And here we assume that this za plus dA plus dF plus dW is equals to dB. Therefore plus dB minus dB get cancelled. Therefore z raised to 0 is equals to 1. Now here dV plus dB, as we have multiplied with the minus dB, therefore it comes out minus d beta plus dV plus dB. Now all the variables in the above relations are polynomials in Z inverse. Now from above all conclusion, we have calculated the degree of polynomials x, that is degree of d of x is equals to d of beta plus k minus 1. How we calculate this degree of x? Previously here you can see from this equation we have calculated degree of x. X is nothing but, we have assumed that this degree of this whole term, that is dA plus dW plus dA, is equals to degree of d beta, and with the help of this minus k, what is the degree of z raised to minus k is nothing but minus k plus 1. Therefore here we have calculated the degree of dx. Degree of dx is nothing but, degree of x is nothing but d beta plus k minus 1. And from further from equation 13.3, what is mean this equation is, this is the equation of for 13.3, and from equation 13.46 and from equation 13. With the help of this property and this property, the equation that is 13.45a becomes as here you can see this is the equation of 13.45, and we have just replaced this all polynomials in star, that is polynomials in z we have to replace in z inverse. Here you can see here we have just replaced all the polynomials. Here w star becomes as wr fr into ar, and here we can assume that dA plus dA plus dF dA plus dW is nothing but d of beta. Therefore we have instead of all these terms, means instead of these all terms, we have just replaced it as z raised to d beta. At the same time these terms remains as it is. We have just put replace this x star with xr, and what is the degree of x? Here we have calculated degree of x is nothing but db plus k minus 1. Here we have just put the value of degree of x is nothing but db plus k minus 1, and b star is also replaced by br into z raised to d beta. That is, we have to use just approach, that is spectral factorization, to convert these z polynomials into z inverse. Now just divide this just divide this all equation with z raised to d beta, and we get the equation. We come up with the equation that is r into br into r1 minus b into xr is equals to rho into w wr fr ar into c. That is, we have just take the common term z raised to d beta, and we come up with this equation. Now we have just previously solved the 13.45a. Now we solve the 13.45b with the spectral factorization property. Now see here you can see this 14.45b equation becomes as z raised to k c into v. This v star, previously this is v star and b star, and instead of this v star and b star we have just write vr into br. Z raised to, we have just combined these terms of v and b. This is dv plus b. Here you have to make change, that is degree of v plus degree of b minus za into f. We have to replace, previously here it is x star, and we have to replace this x star with xr into degree of x. Now here r into b star is previously, now b star is replaced by br into z raised to d beta. Now we are arranging all the terms, and we come up with the equation, that is we have to just here z raised to this z raised to 1 becomes as db plus k minus 1 plus 1, therefore plus 1 minus get cancelled, and it remains with the z raised to db plus k, and we have divided all the terms with the z raised to db plus k. Therefore by solving this equation we get r into br into sc z raised to minus k. That is, once we divide this z raised to b db with z raised to db plus k, we remains with the z raised to minus k. Likewise this equation becomes as zf into xr. Now here we have just z raised to plus k and minus k get cancelled, therefore z raised to dv plus b minus d of beta. We have come up with this equation. Now we have to arrange this 13.49 and 13.50 in terms of matrices. We have to just arrange these two equations in matrices, and the variables are r1 and sc, and we have to just arrange these two equations, and from this we can see that this equation is in the form of Arya-Bhatt identity, and we have to solve this Arya-Bhatt identity to find the unknown polynomials, that is r1, sc and xr. And once we calculated these polynomials, we can design the control effort to minimize the performance index j, and once we have to find these two values, that is r1 and sc and xr, we design the control effort u is equals to minus sc and r1 into f. This is the control effort which is designed to minimize the performance index j in case of LQG controller. This is all about the control design of LQG controller with the help of spectral factorization. Previously we designed the LQG controller, but as we see earlier that the Arya-Bhatt identity consists of lots of complicated solution, therefore we go for simplified LQG controller. And now let's see, this is the two equation which we have taken as it is from the previous LQG controller design. From this two equation we solve the simplified LQG controller. Now we have to multiply this first equation with the a into f, and the second equation with the z raised to minus k into b. With this multiplication we get these two equation. Here you can see we have multiplied this first equation with a, that is here you can see this a and a is multiplied, and at the same time the second equation is multiplied with z raised to minus k, as here z raised to plus k minus k get cancelled, and it comes out to be only b. Here z raised to minus k plus k means here z raised to 1, and z raised to minus k, it comes out to be z raised to minus k plus 1, and the remaining terms here you can see z raised to minus k into b is multiplied to this term. Now after multiplication we have to add these two terms. We have to add this left hand side terms and right hand side terms. Here you can see these two terms are same. Here is plus, here is minus, therefore these two terms get cancelled. We have to just add these two terms. Here you can see we have just add these two terms, and on the right hand side we have just add these two terms. Now as we have seen earlier in the LQG controller design, we have just take common c from this equation, and as we take c common, the terms in the bracket are represented by only b into r into b into beta star. That is, instead of this whole equation, instead of c we have to put r into beta star into c, and the right hand side terms remains as it is. Now we have to just cancelling the common factor of, that is r into beta star is the common term, and therefore we cancelling this term, therefore we remain with the equation, that is here beta into c equals to r1 into af plus z raised to minus k into beta into sc. This is the Arya-Bhatt identity which we have to solve in a simplified LQG controller design to design the control effort u of n. Here you can see from we have to calculate r1 and sc, and from this r1 we have to find rc, as we have c rc is equals to r1 into f, and with the help of this r1 we can find rc, and here sc. We have to solve this equation, we have to solve the Arya-Bhatt identity, and this Arya-Bhatt identity is much simpler as we have seen in LQG controller design. This is a simple form of this array-vector identity, and this array-vector identity is easy to solve. Therefore, we go for simplified LQG controller. Now we can use this simplified LQG controller to design the simplified minimum variance controller. Here we taken the equation. This equation is as taken from the LQG controller design. This is 13.14 equation. This is taken as it is, and with the help of this equation we have designed the minimum variance controller controller. Here you can see another utility of this simplified procedure is that it can be used to design the minimum variance controller when the plant to be controlled is non-minimum phase. That is, the system is non-minimum phase, then we can design the minimum variance controller from the simplified LQG controller. Here we can see when zeta is equals to 0, when this zeta is equals to 0, we come up with the equation that is r into beta star is equals to b into v star into beta star, as where we assume that there is no normalization is done. Therefore we can take as r equals to 1, and at the same time v is equals to 1 as per the convention used in minimum variance control. Due to this equation becomes as beta into beta star is equals to b into beta star. We have to just use the spectral factorization. Therefore beta star becomes as br into z raised to beta. We assume that z raised to z raised to d beta is equals to z raised to db. Therefore we have to just cancel, and we remain with the terms that is b into br is equals to b into, here b star becomes as br into d beta, but z raised to d beta, but z raised to d beta cancel with z raised to d beta. Now we have to split the b polynomials into good factors and bad factors. Therefore we call it as a b is equals to b raised to good g into b raised to bad, g for good polynomials and b for bad polynomials. Now this equation becomes as b raised to g, b raised to b into br raised to g into br raised to b. Now b should have the only stable factors. We extract an stable factor from the right hand side and obtain. Now we should take care that beta should have only stable factor. Therefore beta, for the betas to be stable, we have to take beta as a good polynomials, and as beta is good polynomials, then beta r raised to, as beta is good polynomials, and this beta r into beta r raised to g is have 0 outside the unit circle. Therefore as this beta r raised to g has 0 outside the unit circle, this beta r raised to b, that is bad polynomials, reverse bad polynomial, has its 0 on the unit circle as well as inside the unit circle. Therefore these two terms are taken for the betas to be stable. Here you can see beta raised to g into beta r raised to b into c. We have to just we have to put the value of beta in previous equation, previous array-vector identity, that is this equation. Here you can see this, we have to put the value of beta. Here you can see beta raised to g into beta r raised to b into c. This is the same equation as it is. To design the minimum variance controller, we have to solve this array-vector identity, and from this array-vector identity we can find the R1 and SC, and with the help of these two equation we can design the control effort U of n, and we have to use this control effort to minimize the performance index in minimum variance controller. This is all about to design the simplified LQG controller and simplified minimum variance controller.